We will discuss now the spanning sets and linear independence. We have here first the definition of linear combination of vectors. A vector v in a vector space V is called a linear combination of the vectors u sub 1, u sub 2, up to u sub k in V if V can be written in the form V equals the sum of the products of c sub 1 and u sub 1 and plus c sub 2, u sub 2 plus and so on up to c sub k rather times u sub k, where this c sub 1, c sub 2 up to c sub k are scalars. For example, we have set S containing these vectors in R3. We can observe that V sub 1 is a linear combination of V sub 2 and V sub 3, since we can express V sub 1 as 3 times V sub 2 plus V sub 3. So we have 3, the scalar 3, times 0, 1, 2, which is the vector V sub 2, and plus 1, 0, negative 5, which is our vector 3 or V sub 3. So when we multiply this and then add the results, we will get 1, 3, 1, which is the first vector. So we have 0 plus 1, so we'll have 1, and then 3 times 1, so that's 3, plus 0, that's 3, and then this is 6 minus 5, so we have 1. So we see that our vector 1 or V1 is a linear combination of the vectors V sub 2 and V sub 3. Another example is we have the set of vectors in M22. We have 2 by 2 matrices. So we have these vectors V sub 1, V sub 2, V sub 3, and V sub 4. So V1 is a linear combination of V sub 2, V sub 3, and V sub 4 because we have this V sub 1 is equal to V sub 2 plus 2 V sub 3 minus V sub 4. So we substitute these vectors here. So we have V sub 2 and then plus the scalar 2 times V sub 3 and then minus V sub 4. Now by computing this, we get 0, 8, 2, 1, which is our vector 1 or V1. So again, we see that V sub 1 is a linear combination of these vectors. Now let us have the examples for finding a linear combination. So write the vector W, which is the vector 1, 1, 1, as a linear combination of vectors in the set S. So we have here V1, V sub 1, V sub 2, and V sub 3. Now to do this, we need to find scalar C sub 1, C sub 2, and C sub 3 such that when we multiply these scalars to these vectors, the result will be W or the vector 1, 1, 1. Okay, and then computing this, so we multiply C sub 1 in each of these components and C sub 2 in here and so on, and then add the corresponding components. We have C sub 1 plus 0 C sub 2 and then minus C sub 3. So we get C sub 1 minus C sub 3. Then 2 C sub 1 plus C sub 2 and then we have 0 C sub 3. So we get 2 C sub 1 plus C sub 2. And then 3 C sub 1 plus 2 C sub 2 and plus C sub 3. Okay, so again, this is equal to the vector W. So from this, we can obtain this linear system. So C sub 1 minus C sub 3 equals 1 and so on. Now let us use Gaussian elimination to solve this linear system. So we have write the coefficient, now the augmented matrix rather of the given linear system. So we have 1, 0, negative 1, 1, 2, 1, 0, 1, and then 3, 2, 1, 1. Now recall, the Gaussian elimination. So we'll make ways to make the 0 below this leading one. So we can multiply row 1 by negative 2, and then we add the result to row 2 to get new row 2. So we have 1, 0, negative 1, 1. Then we have 0. We multiply this by negative 2 plus 1, so that's 1. Multiply this by negative 2, so that's 2. And then multiply this by negative 2 and then plus 1, so we have negative 1. Also, for row 3, to make the 0, we can multiply the first row by negative 3 and then add to row 3. So this is 0. This is 2. Multiply by negative 3, so this becomes positive 4. A positive 3 rather, plus 1, so that's positive 4. And then multiply by negative 3 plus 1, so it's negative 2. Okay, and then we'll continue the process. We want this to be 0. So we have 1, 0, negative 1, 1, 0, 1, 2, negative 1. To make the 0, we can multiply row 2 by negative 2 and then add to row 3. So we have 0, 0, multiply by negative 2 plus 4, so that becomes 0. Multiply by 2 and then plus negative 2, so that becomes 0. So since we have here 0, 0, 0, all zeros in the last row, so we have infinitely many solutions. And then from here, from rows 1 and row 2, we have c sub 1 minus c sub 3 equals 1. Then c sub 2 plus 2, c sub 3 equals negative 1. So we can let the c sub 3 as t. So let c sub 3 equals t. So substitute, you will have, then you get c sub 2 equals, is t here, so transpose on the other side. So we have negative 1 minus 2t. And then again, this is t. So c1 is equal to 1 plus t. Therefore, we have the solution to the system. We have c sub 1 equals 1 plus t again, and then c sub 2 equals negative 1 minus 2t, and then c sub 3 equals t, where t is any real number. Now note that we can assign any value to t. Let's say t is equal to 1, then c sub 1 will be equal to 2, and then c sub 2, if this is 1 here, will be equal to negative 3, and then c sub 3 is equal to 1. So therefore, if we substitute that in here, so we have, or we can use the w, so we can write w as 2 times v sub 1. So this is our c sub 1, and then minus 3 v sub 2, this is c sub 2 plus v sub 3. We have c sub 3 equals 1. So we see that w can be written as a linear combination of these vectors. Next example, we have write the vector w. We have 1, negative 2, 2 as a linear combination of vectors in the set S. So we have here v sub 1, v sub 2, and v sub 3. So again, we want to find the scalars c sub 1, c sub 2, and c sub 3 such that we have 1, negative 2, 2 equals c sub 1 times 1, 2, 3, then plus c sub 2 times the second vector, and then plus c sub 3 times negative 1, 0, 1. Okay, so this is equal to, we add the first components here. So we have c sub 1, we have 0 c sub 2, so we have minus c sub 3, and then we have 2 c sub 1 plus c sub 2, and then we have 0 c sub 3. We have c sub 1 times 3, so we have 3 c sub 1, and then 2 c sub 2, and then plus c sub 3. Okay, so these components here of this vector is equal to 1, negative 2, 2. So therefore, we yield to this linear system. So 2c sub 1 plus c sub 2 was negative 2, 3c sub 1 plus 2c sub 2 plus c sub 3 equals 2. Okay, so let us solve this linear system by Gaussian elimination. So we get the augmented matrix of this. We have 1, 0, negative 1, 1. Then we have 2, 1, 0, negative 2, and then 3, 2, 1, 2. Okay, so again, by Gaussian elimination, we can eliminate this, or we can make these zeros by multiplying this by negative 2 and then add to row 2. So we have here 0, 1, and then this is negative, no, rather that's positive 2 because we'll multiply this by negative 2. And then multiply this by negative 2 and then add to negative 2. So we have negative 4. Also, for this one, we multiply this by negative 3 and then we add to row 3. So this is 0, 2, and then we have, this is negative 3, so we have 4, then negative 3, so we have negative 1. Okay. And then next, this is now equivalent to, we will make this 0, 0, 1, 2, negative 4. Okay, multiply row 2 by negative 2 and then add to row 3 to get new row 3. So this is 0, this is 0, and then this is 7. Okay. Okay, so this third row implies that we have no solution. Okay, so the system has no solution. Therefore, W cannot be written as a linear combination of vectors v sub 1, v sub 2, and v sub 3. Now we will discuss the spanning sets. So let S be the set containing v sub 1, v sub 2 up to v sub k, be a subset of a vector space V. The set S is called a spanning set of V if every vector in V can be written as a linear combination of vectors in S. We have V1, V sub 2 up to V sub k. In such cases, it is said that S spans V. Again, the set S is called a spanning set of V if every vector in V, it can be written as a linear combination of these vectors, which is in S. So we say that S spans V. To make this clear, let us consider the following examples. So first, the set S containing these vectors spans R3 since any vector U in R3, we have U sub 1, U sub 2, U sub 3, can be written as a linear combination of vectors in S. That is, we have U, the vector U, equals this plus this plus this, which is again, this is just equal to U sub 1, this is U sub 2, and then we have U sub 3. Because we have zeros here, we have 0 and 0, and then 0 and 0 there. Observe that the scalars here are just equal to the components of U. If U is the vector, for example, 1, 2, 3, then the scalars here will be just 1, 2, and 3. So again, we say that S spans R3. Another example is we have the set S containing 1, x, and x squared spans P sub 2. This is the set of polynomials of degree 2 or less. This is because any polynomial function in this form, which is in P sub 2, can be written as, we have that. Okay, so we have the elements of S. We have 1, x, and x squared. And then we have the scalars, or we have the real numbers a, b, c. So we have p of x here. So again, since we can write each polynomial in p sub 2 as a linear combination of this, then we say that S spans p sub 2. Note that the spanning sets in examples 1 and 2 are called the standard spanning sets of R3 and P sub 2 respectively. Now let us have more examples on spanning sets. So first, we show that the set S spans R3. So we must show that for every vector in R3 can be written as linear combination of these vectors in S. So we let U be any vector in R3. For S to span R3, there must be scalars C sub 1, C sub 2, and C sub 3 such that this vector that represents any vector in R3 is equal to this one. Now this is equal to, we have this, adding this, the components of this. So we get this one. So we have the linear system. Okay, we have this. It's from here. So that's U sub 1, U sub 2, and U sub 3. So recall that in the equivalent conditions given in chapter 2.3, if I am not mistaken, if we have a system AX equals B, where A is the coefficient matrix of the system and B is the constant vector, and the determinant is non-zero, the determinant of the coefficient matrix, say A, is non-zero, then the system has a unique solution. So what I'm trying to say is that we can just solve the determinant of the coefficient matrix of the system, and if we get a non-zero determinant, it would imply that the system has a unique solution. So let us solve for the determinant of the coefficient matrix. We have this. Okay, recall how we get the determinant of a matrix. So we can expand here. We can do cofactor expansion. Let's say in row 1. So we'll have 1. Take note, this is positive, negative, positive. So we can just remove the negative 1 raised to 1 plus 1 there. So we can get directly, we can delete this, and then we get this remaining matrix. And then we have 0 next, so we have plus negative 2 times deleting this row and column, so we have 2, 1, 3, 2. And then solve for the determinant of these 2 by 2 matrices. So this is 1, so that's 1 times 1 plus negative 2 times, this is 4 minus 3, so that's 1. So therefore, determinant is equal to 1 minus 2, so that's negative 1. So again, since the determinant is non-zero, then we say that the system has a unique solution. Therefore, any vector u in R3 can be written as a linear combination of the vectors in S. So we further conclude that the set S spans R3. Next example, we have, does the set S span R3? So we have this set S. So again, for S to span R3, it must be that for any vector u in R3, there must be scalars C sub 1, C sub 2, and C sub 3 such that this is true. Okay? So this is equal to, we have that. So we obtain the linear system. We have this one. Now we write down the corresponding augmented matrix of this system. So we have here 1, 0, negative 1, u sub 1, 2, 1, 0, u sub 2, and then 3, 2, 1, u sub 3. Now let us solve this by Gaussian elimination. So this implies we can make the zeros again. So we have u sub 1, and then this is, we multiply this by -2 and then add to row 2. So that's 0, 1, 2. And then again, we multiply this by -2. So we have -2 u sub 1 plus u sub 2. And then also for this, we multiply this by -3. So this is 0. We have here 2, and then this is 4. And then again, we multiply this by -3 plus u sub 3. Okay, and then we make this 0 here. So to make the 0, we can multiply row 2 by -2 and then add to row 3. So this 0, that is 0, and then again this is -2, so multiply by -2 plus this, so that's u sub 1, multiply that by -2 and then plus u sub 3. Okay, so take note that this last row will indicate if we have infinitely many solutions or we have no solution. So take note that this has no solution if this term here or this element here is non-zero. For instance, let's say we let u sub 1 equals 1. So we have u sub 2. Let's say u sub 2 equals 1 also, and say u sub 3 is equal to 2. Now, if we solve this, you will have u sub 1 minus 2 u sub 2 plus u sub 3. This is equal to 1 minus 2 plus 2. So this is equal to 1, which is non-zero. So this implies that the system has no solution if we have these following values of u sub 1, u sub 2, and u sub 3. So, we say that there exists a vector in R sub 3, for instance, W, which is 1, 1, 2, that cannot be written as a linear combination of the vectors in S. Okay, so since there exists that vector that cannot be written as a linear combination of vector in S, then we say that S does not span R3. Now let us discuss the span of a set. So if S is a set containing vectors v sub 1, v sub 2 up to v sub k, is a set of vectors in a vector space V, then the span of S is the set of all linear combinations of the vectors in S. So we have span of S equals the set containing, again, these are all the linear combinations of the vectors of S. Take note that these are scalars or real numbers. The span of S is denoted by, we can use this or you can use this one. So if span of S is equal to V, it is said that V is spanned by the vector, this set, or the containing v sub 1, v sub 2, v sub k, or we say that S spans V. If we say that span of S is equal to V, this means that all vectors in V are linear combinations of the vectors in S. So again, we say that S spans V. Now we have a theorem which states that span of S is a subspace of V. So if S is a set of vectors in a vector space V, then span of S is a subspace of V. Moreover, span of S is the smallest subspace of V that contains S, in the sense that every other subspace of V that contains S must contain the span of S. For the proof, note that the zero vector is contained in span of S. So span of S is non-empty. Now, we show that span of S is closed under addition and scalar multiplication. So recall, this is how we show that a certain set is a subspace of a bigger space. So first, non-empty, and then we show that that is closed under addition and scalar multiplication. We let U and V be in span of S. This means that U and V are linear combinations of the vectors in S. Okay, so we have this. So take note, this C sub 1, C sub 2 up C sub k, and D sub 1 up to D sub k are scalars. Then by adding these two vectors, we will obtain, we have U plus V equals, we just add the scalars we have here. And for any scalar C, we have C times the vector U. We multiply C to this. So we have C times C sub 1 and so on. So this shows that this show that U plus V and C U can be written as linear combinations of vectors in S. Then we say that U plus V and C times U are in span of S. So this shows that span of S is closed under addition and scalar multiplication. So we conclude that span of S is a subspace of V. So for the continuation, or showing that the span of S is the smallest subspace of V that contains S, will be left to you. So that's an exercise. Now let us proceed with linear dependence and linear independence. So a set of vectors S in a vector space V is called linearly independent if the vector equation of this has only the trivial solution. That means these scalars are only equal to 0. And if there are also non-trivial solutions, so we have solutions other than 0, 0, 0, and so on, then S is called linearly dependent. For example, the set S, we have this, containing these vectors in R2, is linearly dependent because we have negative 2 times 1, 2 plus 2, 4 equals 0, 0. So there are scalars, non-zero scalars, negative 2 and 1. That is, when multiplied to these vectors and we add the result, the answer is 0 vector. Another one is, we have the set S containing these vectors in R2 is also linearly dependent because we can express, or we can multiply this by scalars 2, negative 5, and 1 to yield a 0 vector, or 0, 0. So again, we have non-trivial solution, so this is linearly dependent. Another example is, we have, again, this set is linearly dependent because we have here other solutions other than 0, 0. So we have 1 times this vector plus 0 times this vector equals 0, 0. So we have the scalars 1 and 0 that is, when multiplied to these vectors, will yield to the 0 vector. So again, this set is linearly dependent. Next is, we will discuss how to determine whether a set of vectors is linearly dependent or linearly independent. So we have these steps. So let S be a set of vectors in a vector space V. To determine whether the set S is linearly independent or linearly dependent, we perform the following steps. First, from the vector equation, so we use the given vectors in the given set. multiply them by scalar c sub 1, c sub 2, and so on, and add the result, and then equate it to 0. So write a homogeneous system of linear equations in the variables c sub 1, c sub 2, up to c sub k. And then next, you use Gaussian elimination to determine whether the system has a unique solution. So if the system has only the trivial solution, then the set S is linearly independent. However, if the system has non-trivial solutions, then the set S is linearly dependent. So to illustrate this, we will do the following examples. So first, determine whether the set of vectors in R3, so we have the set S, is linearly independent or linearly dependent. So to do this, we need to find scalar C sub 1, C sub 2, and C sub 3 such that we have that. We substitute now the vectors v sub 1, v sub 2, and v sub 3, and then multiply to these scalars and add the corresponding components. So we have this equal to 0, 0, 0. And then this will yield to the linear system. We have this. Note that if this system will only have the trivial solution, then the set S is linearly independent. If there are non-trivial solutions, then S is linearly dependent. So again, to solve this linear system, we will use the Gaussian elimination. So we have 1, 0, negative 2, 0, 0, 3, 2, 1, 0. Okay, so same process as we did a while ago. So we'll just make the zeros. So we have multiply by negative 2 and then add to row 2. So that's 1, 4, and then 0. We multiply by negative 3 and add to row 3 to get new row 3. So this is 2, negative, so this is negative 3, so that's 6, so 7. And then we have 0. Okay, and then continue the process. We have 1, 0, negative 2, 0. Sorry. That's 0, 1, 4, 0. And then to make this 0 here, we multiply by negative 2 and then add to row 3. So that's negative 1, 0, which is equivalent to okay. So we have this matrix. So this shows that the system has only the trivial solution because we have 1 here. So that's C sub 3 is equal to 0, and then substituting that value to the here. So we get C sub 1, C sub 2, C sub 3 equals 0. Okay. So since we have only the trivial solution, then we say that S is linearly independent. For our next example, we have determined whether the set of vectors in T sub 2, again, this is the set of polynomials of degree 2 or less, is linearly independent or linearly dependent. So we have the set S here. Okay, so again, we want to find these scalars C sub 1, C sub 2, and C sub 3. And then we want to know if we have only the trivial or the non-trivial solutions. So substitute the values for or the given vectors, v sub 1, v sub 2 here, v sub 3. Then equate to 0 plus 0x plus 0x squared. So we have that. So just continue solving this. So just add the corresponding components. So we get the linear system. We have this one. And then by solving using the Gaussian elimination, so you can verify this. So this is the augmented matrix, and then you can verify that this can be reduced to this matrix. So we have here 0, 0, 0. We have zeros in the last row, so that means we have infinitely many solutions. So therefore, since we have other solutions other than 0, 0, 0, then we say that S is linearly dependent. Okay. One more example we have. Determine whether the set of vectors in M sub 2, 2, this is the 2 by 2 matrices, is linearly independent or linearly dependent. So we have the S here. So this, we just follow the same pattern of solution. So we find C sub 1, C sub 2, and C sub 3 such that we have this as equal to 0. Then substitute. We have the vectors V sub 1 to V sub 3. And then by multiplying these scalars here, so this will be just C2, C sub 1, C sub 1, and then 0, C sub 1, and so on. And then we add the corresponding elements here, and then equate to 0, so we yield to this linear system. Okay, so this is 2C sub 1, so the A sub 1, 1 position, plus 3C sub 2, and then plus C sub 3 equals 0. And then C sub 1 plus, we have 0, 0, so that's just equal to 0. And then 0 C sub 1, so you may not write that one anymore. So 2 C sub 2 plus 2 C sub 3 equals 0, and so on. Okay, so by solving using the Gaussian elimination, we yield to this. So you can verify that this matrix, augmented matrix of this linear system, is equal to this one. Okay, so this shows that we have here the unique solution. So we have this part here is C sub 1 equals 0, C sub 2 equals 0, and C sub 3 equals 0. So since we only have the trivial solution, the 0, 0, 0, then we say that S is linearly independent. Next, we have a property of linearly dependent sets. So a set S, where we have K is greater than or equal to 2, is linearly dependent if and only if at least one of the vectors V sub j, so one of the vectors here, can be written as a linear combination of the other vectors in S. For example, given the set S, this set S is actually the given in example 2, and we have shown that this is linearly dependent set. Now let us show that one of these vectors can be written as a linear combination of the other vectors. So let us go back a bit. So we have, okay, so this is the set S. And then we have shown that the set S is linearly dependent, and we have this row echelon form of the augmented matrix of this system. Now from here, we see that we have from this matrix, we have C sub 1 plus 2 C sub 2 equals 0, and C sub 2 plus 1/3 C sub 3 equals 0. So again, we have infinitely many solutions. So we can have a free variable, or we can let C sub 3, let's say 3t. So if C sub 3 is 3t, that will be cancelled out, 3. So we have C sub 2 is equal to negative t, and substituting this in here, so we have C sub 1 is equal to 2t. Okay, and then if we let t equals 1, then we get C sub 1 equals 2, C sub 2 equals negative 1, and C sub 3 is equal to 3. So we have, by substituting this scalars, so we can have 2 v sub 1 minus v sub 2 plus 3 v sub 3 equals 0, and this will imply that v sub 2 is equal to v sub 1 plus 3 v sub 3. So we see that v sub 2 can be written as a linear combination of the vectors v sub 1 and v sub 3. So we can check this using the given vectors. So we can have 2v sub 1 plus 3v sub 3 equals 2 times, then plus 3 times v sub 3, we have x plus x squared. So this is equal to 2 plus 2x minus 4x squared, and then plus, this is 3x plus 3x squared, and then adding the like terms, we have here 2 plus 5x, and then negative x squared, which is equal to v sub 2. Okay, so let us go back to our example. Okay, we have shown this theorem in this example. Okay, so again, we have that. So we have, this is linearly dependent, and we can write v sub 2 as linear combination of these vectors v sub 1 and v sub 3. Next, we have this corollary. Two vectors u and v in a vector space v are linearly dependent if and only if one is a scalar multiple of the other. Again, u and v are linearly dependent if and only if one can be expressed as a scalar multiple of the other. For example, we have the set S is linearly independent since v sub 1 and v sub 2 are not scalar multiples of each other. So you cannot find scalar c, for example, that when multiplied to v sub 1 will be equal to v sub 2 or vice versa. So we say that this is linearly independent. However, for this given set, we see that your vector 1, v sub 1, is equal to negative 2 times this vector. So times negative 2, so that's 4, times negative 2, that's negative 4, times negative 2, so that's negative 2. Since we can express v sub 1 as the product of v sub 2 and negative 2, then we say that S is linearly dependent. Okay, and so that's the end of our discussion for lesson 3.3 rather.